Good morning. I got a lot of information to go through this morning, so I'm assuming since you're here at 8 a.m. on Thursday, you're diehard. So I'm gonna go through this pretty quickly. Feel free to follow up with any questions. Email me any questions after this. So this was a pooled fund study that we did in the Midwest. We had 12 states participating. I really have to give a ton of thanks to my previous boss, Bill Oliva, for collaborating, bringing all these states together to work on this project. Our principal investigator for the project was WSP. It was Wood Environmental when we started, but then transitioned during the process. So this was one of those 2-year studies that went for 3 years, but it was completed last November. So the big emphasis was pooling our resources, and especially our data as Midwest states. So when Wisconsin started looking at creating deterioration curves with our AASHTO elements, there wasn't a lot to work with, right? Not a lot of inspection cycles. So pooling our data was one of the ways where we could get more reliable curves faster. So we went after both the component MBI rating, deterioration, and elements, and then really looking all the way to our bridge management systems, trying to get more accurate predictions coming out of there based on the data. So this was the list of tasks in the research study. Typical literature review, starting with a raw data set, everybody just dumping their data, and then the researcher tailoring that to an analysis data set where we could pull specific models for specific elements out of there, and then a review of the models. So like any research project, you get a little bit ways into it and then you have to circle back. So what we found is we all kind of talk the same lingo when we get together at conferences, and then when we dive into our databases and our actual inspection practices, it's like, whoa, that's a lot different than what I thought. So here's a little overview of deterioration modeling. We ended up going with a typical Markov-Weibull deterioration method. It seems kind of industry standard. A lot of the states use BRM, so that's the deterioration model that BRM uses. That's what we ended up going with. Anyways, the red X's here show the typical Markov curve, and then different factors can modify the shape of that curve depending on what you're trying to achieve. And the typical modification factor is the Weibull factor. So a few different components that were involved: linear regression for transition probability, the Florida one-step method. So the Markov modeling has this whole probability matrix, but the Florida one-step essentially says we're gonna just assume that element is deteriorating constantly from one state to the next. So it simplifies the calculations a lot. Maximum likelihood estimation, that comes into play with the Weibull factor. We also use that for we tried to pool all our construction history, and it turned out that some of the states didn't have a very good data set for construction history, so we ended up having to use a modification factor on that first transition from condition state 1 to condition state 2. Here's an overall look at the bulk numbers, I guess. So over 200,000 bridges amongst the states, almost 2 million routine inspections using MBI values, almost 400,000 routine inspections with the new AASHTO elements, about 100,000 inspections with AASHTO element defects. I know some states don't use the defects. We had about 200,000 construction activity entries, and like I said, that was still a little bit short to have a complete construction history. We gathered about 9,000 NDE inspections, and amongst the states there were about 400 agency-defined elements. This is just a brief shot at some of the tables that were in the final analysis data set. It closely resembled the BRM tables, since that's what most states were using, with additions of some other tables. Wisconsin DOT is the actual data custodian for the entire data set, but other states have access to that data as well. So that's the main point of that one. Again, the deterioration curves used Markov. In the final spreadsheets that we got for each model, that could be dynamically adjusted based on different factors that are in that spreadsheet as well. The viable factor used maximum likelihood. That was kind of a static calculation. Sometimes that had to be calculated based on a larger element set, and then the same viable factor was used for different subsets of that same element. And then action effectiveness, that relates to that construction history factor. So again, the Markov procedure started with the larger data set. SQL pulled those into specific inspection pairs within the table. We incorporated the work activities. We stratified the data set with inventory values so that we could have that adjustability. When we looked at each element, we could pull out different factors like ADT and stuff like that. Throughout the study, we divided it up into 3 tiers, just because we knew we were trying to tackle a lot, and if the principal investigator wasn't cutting it for tier 1, we were going to cut them for tier 2. But they did well. So Richard Bodie, the project manager right now, is sitting in the audience, so he's laughing. He did well. He made it all the way through. So tier 1, we went after the NBI component ratings. With 12 different states, we're all at different levels of our asset management implementation. So NBI was key for some of the states, but then we did get right into the elements with reinforced concrete deck and slab. And then we did look at residual effect of maintaining reinforced concrete deck. And then tier 2, we got into some of the smaller elements. Wearing surfaces was a big one for Wisconsin. We make sure to have a wearing surface element on all of our bridges so we know what's going on the top of the deck versus what's going on the bottom. And a few other things I'll get into later. So here are some of the results. Early on, if you remember that number before of like 2 million NBI inspections, that was a lot of inspection pairs. So we did do a random sampling of NBI inspections, but we did make sure it was state-owned bridges with traffic and non-buried structures. So kind of the more deteriorated structures that we were going after. So here's just a breakout of the deterioration of deck, super sub, culvert. And since we did connect it to inventory values, we were able to, change up the graphs, look at the effect of different types of preservation strategies. Here, this shows just the deterioration of deck NBI for epoxy-coated rebar decks versus black bar. Here's superstructure NBI just broken up by span type. So pre-stressed girders versus our reinforced concrete slab versus steel girders. Here's reinforced concrete slab ratings, looking at both the deck NBI and super NBI. So right now we have a policy to have the same NBI for both. So I was just checking to see if the data came out. Apparently, that wasn't a historical practice, so that shows a little bit difference between the deck NBI deterioration and the superstructure. So now getting into a bunch of the tables. So reinforced concrete deck element, this slide is all about reinforced concrete deck elements, and see if I can get the pointer here. So the emphasis here, if you're not familiar with Markov modeling, it's highly dependent on median transition times. So the key numbers in these tables are T12, T23, T34. So that first one, T12, that's the average number of years it takes for 50% of condition state 1 quantity to move to condition state 2, and then so on down the line. So that first table in the upper left, that was just statistical validation to random sampling of the data set, just to make sure it was homogeneous, and it checked out for each of the models that we created. And then you can see a breakout of like by construction era, that was year built, and you can see the changes in the average transition times there. And then by traffic volume. What I really think is interesting and what highlights the value of the study is this larger table on the right. You can see the variability between all of the states that were involved, and we all had different amounts of data, I know, for each of these elements. And you can see some really wacky numbers at times. But because we went through the effort of pooling our data, you get some pretty good numbers at the end. So that's the final numbers there at the bottom. And this is just the Weibull calculation for reinforced concrete deck. Here you can see, a scatter plot of all the different amounts in fraction in condition state 1. The gray were data points that were eliminated, so this is the maximum likelihood method, and then there was essentially just a best fit curve applied to that. So when we got into the reinforced concrete slab element, here's just a graph showing just general health index, showing reinforced concrete slab outperforming reinforced concrete deck, which we would expect. And it's nice also that it correlates with our NBI rating deterioration between reinforced concrete deck and slab. Tier 1 also included looking at the effect of major preservation on our reinforced concrete decks. So these are both do-nothing curves, but it shows some residual benefit to performing preservation on your decks in a consistent manner. So diving into Tier 2, the mentality here is to kind of, make our bridge management system more functional, right? So NBI is great for communication, high-level communication, distributing funding, stuff like that. That's great. Safety inspections. Bridge elements are great for helping us know where to perform the work. And then element defects, which we also included in Tier 2, that really helps an automated bridge management system look at the data and know exactly what work needs to be done on that specific element. So I view this as a key part of an automated bridge management system that is focused on bridge preservation, because then it gets down to that level of detail that you want. First off, wearing surfaces, this is just a general, that yellow curve is just a general deterioration curve for all wearing surfaces. Not very helpful to us in Wisconsin, but might be for some others. But then it also shows the effect of a protected deck with a wearing surface versus an unprotected deck. When we went after the wearing surface types, we created these kind of research groupings from some agency-defined elements, and then or typical practices within certain states. For states that didn't have agency-defined elements, we used NBI item 108 to translate the wearing surface element data into that research grouping. So from that, we could actually create deterioration curves for the wearing surface itself, which is just the top of the deck. Here's the straight Markov model, and that's with the Weibull factor of 2.2 applied. And then we can break it out and look at, condition in each condition state over time as well. Tier 2 also included joints. The researcher noted that they deteriorated a lot quicker than even previously expected. You can see 5 years transition time from 1 to 2 for strip seal expansion joints. It doesn't give us a lot of time, but you know, a lot of inspectors are diligent about recording leaking starting to occur in those joints. So that reflected in the new deterioration curves. And then there was one viable factor calculated for all joint types, and that was around 4. This one was really interesting. It was a question we had in Wisconsin that we wanted to explore in more detail. We always know that cracking is going to lead to delamination sometime in the future. And so we wanted to kind of set a precedent of like, well, how does that change the likelihood, right? This is what the researcher came up with. They have a health index on the left side of this table here, defect 1130, and it combined condition states 1, 2, and 3 within that factor. And I got an example on the upcoming slide. Overall, we showed a lot of slow development, a lot of decks that stayed the same over that analysis period. But there was a strong relationship to deck cracking as expected. So just taking condition state 2, trying to simplify it here. So that factor of up to 1.0, it's essentially decks that have 0 to 6% of CS2 cracking. And you can see a median transition time there of around 30 years. So then if you go up to the next level, up to 0.98 for that factor, that's roughly 6 to 60% of your element has CS2 cracking. So a lot more cracking, but then you can see that you're twice as likely in that state to develop delaminations. So this was just kind of the first take of where can we go with the data. There isn't an automated bridge management system that can use this right now, but we're kind of testing the waters here. Tier 2 also looked at paint system defects, and I wanted to kind of balance that of like a kind of a check within the data, our paint system condition versus steel girder corrosion. And these are 2 tables that used that same kind of health index factor and looked at the effect of both of those. Reinforced concrete substructures. This was interesting to note. So they're all very similar between pier caps, abutments, pier walls with their transition times until you get to columns. And the researcher noted that it's probably the way we're collecting them, right? You collect something by each, it's just naturally less granular than by linear foot. So you got to be aware of it's going to affect your transition times then too. With reinforced concrete substructures, one thing we were interested is knowing that kind of that threshold of are you creating a harsh environment. The closest thing that we got to correlate with that is ADT under the bridge, and then there you can see at an ADT of greater than 10,000 would be a drastic change in that deterioration. So that would potentially be a threshold where you would apply a different deterioration curve for those specific structures within your inventory. Tier 3, we were hoping for a little bit more analysis out of Tier 3, but it turned out to be more of kind of a survey of what's going on amongst the states. We identified useful agency-defined elements that were used amongst the states, determined which elements might be promoted further, provided guidance on best practice of data collection, gathering, formatting, stuff like that. And then we determined the status of NDE efforts or programs, and then also included NDE translation. So what you get from results from NDE, how does that translate into actual inspection quantities? So wearing surface ADEs throughout all of our conversations turned out to be a pretty big deal. So it was really helpful when agencies had defined elements for their wearing surfaces. It unmuddied the waters of what is your true deck condition. When you're trying to overlap top and bottom defects for the same element, we don't know whether to do a concrete overlay or a redeck. So having an agency-defined element for the wearing surface was very helpful. And this is a snapshot from our Wisconsin field manual for inspection. We make the note of the wearing surface goes down to the top mat of steel just to make sure any delaminations we find with thermography or chaining get recorded into that top wearing surface. Defects were also very helpful. So I know they're not required, but they were very helpful in our research. So just a list of states that have defects and don't have defects, and just another snapshot of defect examples. For NDE, a lot of states just perform it as needed or on a research basis. Not many had a network level program. In Wisconsin, this is just a chart of what we're doing and a breakout of IR versus GPR, chloride ion, and then chaining. Okay. And then this is just how Wisconsin currently translates between NDE and condition state quantities. So the main recommendations coming out of Tier 3 were to work on a more uniform way of assessing deck condition with defects and wearing surfaces, and also a format for recording construction history, so we have a more consistent record. With the implementation, it was mainly geared towards BRM users. We were able to link up with a user group meeting for BRM and talk through some of the implementation challenges there. Like I said earlier, some of the results are too advanced for current BMS software, but we were talking with Mayview about different ways to enhance what BRM does. The models can be stratified based on different inventory values, but you need to take care that you don't get that data set too small as you're looking for a specific type of structure. All the models can be updated. Wisconsin already went through an effort with WSP to update based on our current inspection data. So we have a little bit more updated models than from this study. And then additional elements can use the same process we used in this study to generate additional deterioration curves as needed. And then here's just a chart from BRM showing kind of when you're implementing a new deterioration curve, you can see the difference between what you've already got in the system and then what you're going to be implementing. Okay. And then there's always room for future research. We tried to cover a lot of ground in this one study, so there's a lot of different ways that we could improve from here. Thank you.
I think, do we have time for any questions? A quick question? We'll take one question. If not, oh, we have one right here.
Can you explain a little bit about the health index? Like what percentage are you looking at as like end of life or, because I know like a 3 is end of life, but if, in terms of health index, what percentage is like replacement?
So in Wisconsin, we don't really look at a health index. We will look at, basically, we take our knowledge of what we program off of, right? And it's different for every state. We'll look at a certain defect, like we want to fix delaminations in our deck. And so we'll look at a certain threshold for delamination, and that will trigger a concrete overlay in our system. And so it's looking for those specific trigger points based on your current policy that you have, and just, taking all that knowledge that everybody has and just write a rule for it. Yeah.